Yes, good afternoon, class. We want to go to the application of circumference stroke perimeter. In our previous lesson, we saw how we could get the circumference of circular objects, and we used the formulae. Circumference C is equal to 2 pi r when radius is given, and also or circumference is equal to pi d where diameter is given. So we also appreciated that if we want to find the circumference of a portion of a circle, for example, a quarter of a circle, we found that for a quarter of a circle, perimeter P is equal to pi r over 2 plus 2r. That is for a quarter of a circle. For a half circle, half of a circle, we found that perimeter P equals to pi d over 2 plus d, because diameter is given when it comes to half circle. And then 3/4 of a circle, we had 3/4 of a circle. So perimeter P was given by 3/2 pi r plus 2r. This is 3/4 of a circle. That is what we looked at in the previous lesson. So we want to look at the application on that. We just want to look at the application on that. Where do we apply all this? Sometimes we have shapes and figures that combines circles, rectangles, semicircles, quarter of a circles, and any other shape that we'll want to define in life, especially when it comes to building and construction. You might have a window constructed in terms of the top part, for those like in the church. We have windows whose upper part is a semicircle and the lower part is a rectangle, like that. So this is a figure which is constructed using combination of two shapes. The upper part is a semicircle, the lower part is a rectangle. And in this case, we can now find the material that is required to make this particular kind of a structure. So to find the material, the length of the material that is required to make this particular kind of a structure, we must put into consideration the formula we've learned. For the upper part, we shall use the formula for a semicircle. For the lower part, we shall use the formula for finding the ordinary perimeter of plane figures. So those are areas where we can find application in that. We also find application when we are making, let's say, decorating our houses. When we are manufacturing objects, we use all these shapes and figures in designing a particular model that is appealing and aesthetically appealing to the human eye. So let's look at just numerical applications on that. Like I have a figure here. Find the perimeter of the composite ship to 2 decimal places. Example. Find to 2 decimal points. Find the perimeter of the composite shape to 2 decimal points. When we talk about composite, what it means, this figure combines 2 different shapes or more, 2 or more different shapes in one figure. And that's now what we call the composite shape. For example, it can be a shape that combines a triangle and a semicircle, a shape that combines a rectangle and a triangle, or a shape that combines both rectangle, triangle, and a portion of a circle. So let's look at this. So this is what we call the composite shape, because if you look at the first part, it is the shape is a what? It's a triangle. It's a triangle, a right angle triangle. And the second shape is a semicircle. So this is now what we call the composite shape, which is a shape made out of 2 figures, the triangular figure and the semicircular figure. So to get the perimeter, we use the concept that we have learned earlier to get the perimeter. For example, we shall get the perimeter of the semicircular part and get the perimeter of the rectangular part. But remember, perimeter, we are only talking about outside length. When we talk about perimeter, we only talk about outside length. So I'll move from A to B, then B to C, and then to D, which will be the semicircular part. And then from D to A, I'll have completed my journey. When I started from A, I came back to A. That's now what we call perimeter. The dimensions are given. This is 5 centimeters. We have been given the distance from that point to that point is 2 centimeters. Not so 2 centimeters, but 2 meters, sorry. 2 meters. 5 meters. 2 meters. This one here is 3 meters. So I start by finding the circumference of the semicircular part, which is a circumference so look at that. It is 2 pi r over 2. Why? It is because it's a semicircle. So I find the circumference of the circle, then I divide by 2 to get the circumference of the semicircle. So this will, by substitution, we shall get these 2 by 2 goes, so we get pi r. So I substitute and get C is equal to 22 over 7 times 2, because that is the radius. That is our radius. So it is 44 over 7. So it's approximately 6.29 meters. So our C is equal to 6.29 meters approximately, because we have been told to give the answer correct to 2 decimal points. Then I know the distance BCD is 6.29 meters. So I find the circumference now. Now I start from perimeter. Now will be perimeter of the composite figure will now be equal to 3 meters plus 6.29 meters plus 5 meters. They are only 3. A to B is 3 meters. B to B, C, D is 6.29. and then D to A back is 5 meters. So when I add the 3 dimensions, I get 14.29 meters as the perimeter of the figure. 14.29 at the perimeter of the figure. So some will say 14.28 by truncation, which is no problem. But if you round off the upper part, you get 14.29 meters, correct to 2 decimal places. Let's look at another example on the same. There's another example here. Example 2. Now, if you look at this figure, you will now appreciate that while this is the center of the circle, and this point is A, and this point is B, this is an enclosure. And to find the perimeter, we must find the perimeter of A round to B, and then B to A. That's when we shall have calculated the perimeter of the circle. This one is 2 meters, and the mathematical appreciation on that is that this one here is equal to that, meaning that this is a radius. So this is 2 meters. 2 centimeters. Yes, sorry. 2 centimeters. 2 centimeters. This is 2 centimeters. And this is 2.8 centimeters. So to get the perimeter, we must first of all find the distance A round up to B, then from B to A. So if you look at A, from A to B is 3/4 of a semicircle. So since arc AB defines 3/4 of a circle, then C is equal to 3 over 2 pi r plus 2r. This is from what we derived earlier on in our previous class. So from here, we know R. R is 2 centimeters, so we can easily substitute and work out the circumference from A to B, which is 3/4 of the circle. So this implies that is how you do it. That is our radius. So you simplify what is in the bracket. So this one gives you C approximately equal to 9.43 centimeters. So from A round to B is 9.43 centimeters. But there's the remaining distance, which is what? 2.8. So we add to get the perimeter. We add. So you add to get the perimeter. So it's equal to 9.43, which is this distance A round plus BA. And that gives you 12.23 centimeters. That is the perimeter of that figure. So the perimeter of the figure is 12.23 centimeters. So what we must do in perimeter you must add all the distances within an enclosure. So those distances that are marked with straight continuous lines, dots, are the ones that we add, and that's where we have gotten 9.43, which is the arc, outside arc, plus distance BA. We shall have completed the perimeter of a circle. Now we want to look at now, why do we learn circumference and perimeter of objects? Now I want to give one application question where we can apply perimeter and circumference. In the motor vehicle industry, we manufacture vehicles, that is small cars. We have big trucks, and any kind of a vehicle is manufactured using a particular engineering, mathematical modeling. For example, when you want to make the tire of a car, a saloon car, the first consideration that we must give priority is the radius and the diameter of the wheel of the vehicle that we have manufactured. That one will also define the speed at which that vehicle will be moving, so that you can be able now, when we now manufacture the speedometer of a vehicle, we know that when this vehicle is moving at 60 kilometers per hour, the tire will be revolving at this particular number of revolutions per minute, per hour, per second, and the like. So if you're driving your vehicle, let's say at 80 kilometers per hour, or 60 kilometers per hour, or 120 kilometers per hour, know that the tire of that vehicle is revolving. The number of revolutions that the vehicle is making is dependent on the engine revolution. So let's look at an example on that. Now look at this question. This is now what we are talking about, application questions. David wishes to build a circular fish pond. The diameter of the pond is 3 meters. How many linear meters of bricks are needed to surround it? So what this one means, the first thing that you must appreciate here is that the shape of the pond that we want to construct is a what? It's circular. So the shape that comes into my mind is a circular what? A circular object, like this one here. Then the information I'm given is that the diameter is 3 meters. So diameter, 3 meters. Just like that. So it means if I want to find the circumference will be equivalent to the linear meters. So you can see here, the concept here is linear meters. Linear means length. So when I'm talking about linear, I just basically mean length. And that length, we translate it from the circular path into the meters. And that one can only be found when we find the circumference. So definitely I find circumference of the pond. Circumference of the pond. C is equal to, pi d. Why? Remember we said in our previous lesson that when we are given diameter, we use pi d because d is twice r from the relationship that we derived earlier. So this implies that C is equal to 22 over 7 times 3. So you get our circumference as 9.428 meters. That is our circumference. So that's our circumference. And that one translates into linear meters of bricks that we need to surround when we are constructing the pond, to surround the pond with. That is the first question. So how many linear meters of bricks are needed to surround the pond? And that is, we get 9.428 meters. So we have found the linear meters of bricks that we need to surround the pond. Part B of the equation. So look at part B of the equation. Now it is costing. The first part we were asked the linear meters of bricks that we need to surround the pond. Part B of the equation is now costing. What is the cost if the bricks are $45 per meter? So if 1 meter is $45 and we needed 9.428 meters to surround the bricks, then what we'll do, we'll multiply. So it will just be a multiplication, because 1 meter of the brick cost $45. So 9.428 meters will cost what? So we ask ourselves that 1 meter equals to $45. And we want 9 point. So we just multiply 45 by 9. This will give us the cost, implying that cost is equal to 9.4 times 45. So our cost, which you will get as you will get $4,242.6. That is the cost of constructing this particular pond. Now look, you see now that is now application from what we have learned in perimeter. Let's look at another example. Another example and application. So look at this question. This is now in motion. The wheels of a bike have a diameter of 1 meter. Part A of the question, how many meters will the bike travel in one full turn of the wheels? When the wheels rotate once, how many meters will it travel? So that is basically circumference of the wheel. So because the wheels are circular, we basically work out circumference. So we shall say circumference of the wheels describe one full turn. We have been told that diameter is 1 meter. Because we have been given diameter, we use the formula pi d, and that gives us 22/7 times 1 meter. we have been told to give our answer correct to 2 decimal points. So we leave it as 3.14 meters. So when the wheel turns once, the wheels cover 3.14 meters. That is the linear distance the bike moves. Part two of that, knee in 15 full turns. Fifteen full turns means the wheels rotate 15 times, and 1 turn is 3.14. So this implies (15 times 3.14 meters). This is the distance that will be covered by the bicycle, and that gives you that will give you 47.10 meters. So the bicycle will cover 47.1 meters when it turns 15 times. Part B of the question, how many kilometers? So look at this question now. This is an application of, we want now to translate what we have been looking at, circumference, into linear distance. But now we are told it is 1,000 full turns of the wheels. That means if the wheels rotate 1,000 times, we translate that distance now from meters into meters. And because you have learned measurements, in year 8 we learned how to convert units of measurement. Remember we say that the SI unit of meters, the SI unit of length is what? Meters. SI unit of length is meters. So we must now be able to convert meters into kilometers. And we had the relationship also that stated that 1,000 meters is equal to 1 kilometer. So we say that for solution, one complete turn, one full turn, one full turn is equal to, for one full turn we had calculated to and found that for one full turn the wheels rotate 3.14 meters. So we multiply 1,000 full turns by 3.14. Which gives us so if the wheels of the bike rotates for 1,000 turns, the distance covered in meters is 3,140 meters. And because 1 kilometer is equal to 1,000 meters, and this one gives us 3.14 kilometers. So if the bike rotates for 1,000 complete full turns, it will cover 3.14 kilometers. That is how we apply that question. Then finally on that application, we just look at one example, then we go to another part of measurement of circumference. Example 3. Now, what is the minimum number of times a wheel of a diameter of 1 meter needs to spin? Now, the concept there is to spin. That is a new term that we have seen. So the word spin means a revolution, yani a turn, one turn. So the number of times the wheel turns, that is what we call spinning. So to spin means moving many times or revolving or rotating many times. So the diameter is 1 meter. So first of all, we must find circumference. For our solution, step 1 will be find the circumference of the wheel. Because you have been given diameter, so circumference C, you use pi d. So you get circumference as 3.14 meters when you use pi d. This is one spin, but we have been told that the distance we need to cover is 1 kilometer. That is the distance. So if we know distance and we know one turn, which is 3.14, then we can find the number of spins. So distance is 1 kilometer, which is equivalent to 1,000 meters. And one turn is 3.14 meters. So you can now see that number of turns is equal to distance over circumference. Distance over circumference. So we are able now to substitute and get that. We get 1,000 over 3.14. And that gives you we get approximately 318 turns. That is the number of turns that the wheel of the bike needs to turn so that it covers a distance of 1 kilometer. So you can see now, these are now applicable application questions when it comes to diameter and calculation of circumference of circular objects. Now I want to look at now what we call arc length. This is the last part of this. I want to look at arc length in relation to circumference of circles. Now class, you'll appreciate that when we're introducing circumference and arc and portions of a circumference, we did say that this is just a reminder that circumference of a circle we define it as 2 pi r, where r was the radius. That is for a circle. 2 circumference of a quarter of a circle. We define it as C equals to pi r over 2 plus 2 pi r. That was the circumference. 3 was defined as C is equal to pi d over 2 plus d. This was from our previous lesson. So we have to appreciate that while we defined that, these were portions from part 2 up to part 4. This is 3/4. Now, we want now to translate this to a general format that will guide us anytime that we are asked to define circumference. We will be able to apply that general formula so that even if it is not a semicircle, we can get the arc length. So you can appreciate that for the first part, this part was the arc length for the quarter of a circle. This part was the arc length for the semicircle. This part was the arc length for 3/4 of the circle. So the first part here, for the quarter of a circle, we had something like this. So you can appreciate that this part defined this particular arc length. That's now what we call arc length. For this one here, we had something like this. So this part, the part that I've circled, defined this portion here, the semi-circumference. This is quarter of the circumference. And for this one here, we had this. So this part here defined this portion. So we want to develop a general formula that will be able to guide us. Suppose the portion of the circle we are given is not a quarter, neither is it a half, nor is it 3/4. What do we do? This is our starting point. In year 8, you were introduced to the angle properties of figures, including angle properties of circles. Now, if we have a circle of radius r, we have a circle of radius r, and another radius is drawn from point A, from point O to point B. Then OAB forms an angle at the center. OAB forms an angle at the center. This angle formed at the center is part of the angle of is part of the total angle in a circle, and we know that the sum total angle of a circle is 360 degrees. Sum total of all is equal to 360 degrees. So it means therefore that if we just have, you can now see that AB, this radius, they give out a portion of a circle, which is this. This portion is neither a quarter, it is not a half, it is not 3/4 of a circle. It is just a portion. But from the definition, our previous definition, we say that we can find those arc lengths for a quarter, a half, and 3/4. Now let's look at the angle formed by a quarter of a circle. The angle formed by a quarter of a circle. We say that that angle is 90 degrees. That will be a quarter. So if it is 90 degrees, 90 degrees is just but a portion of 360 degrees. So we shall take the angle formed by the portion of the circle over the total angle, multiply by the circumference of the circle, and we get the arc length. So we say arc length will be equal to, for a quarter of a circle, it will be 90 where 90 is this angle here. 360 is the total angle inside a circle. So let's simplify this and see. By 0 and 0 will divide. By 9, 1 by 9. No, sorry. There's a mistake. It will be 90 over 360. 90 over 360 into 2 pi r, where r is the radius of the circle and the whole 2 pi r is the circumference. So a quarter of the circumference will be 90 over 360. So when we do that, it will be 1. This will be 4. This gives you a quarter into 2 pi r. If you introduce a quarter inside the bracket, you get pi r over 2. And this is the portion, the arc length, when we are talking about a quarter of a circle. Let's look at a half. Let's look at a half circle. We know that for a half circle, the total angle on a straight line is 180 degrees. So the total angle on this line will be 180 degrees. So I want to find the arc length. So arc length will be is equal to 180 all over 360 into 2 pi r, where 2 pi r is the circumference. By 181 by 182. So what do we get? We get pi r. And this is the circumference over the arc of a semicircle. The arc of a semicircle is pi r. Now let's look at 3/4. Oh, a half. So we get 180 over. So for a half a circle, this is 180 degrees into 2 pi r. So this will be 1, this will be 2. When I distribute a half inside, I get pi r. This is the circumference of half of the circle. So you can now see we are now developing a basis on which we want to have what we call a general argument that will guide us in any case we want to find the arc length over a circle which is not a quarter, which is not a half, and which is not 3/4. Let's now move to 3/4 and see what will happen. For 3/4 of a circle, this is the angle that has been removed. So it means that if we remove 90 degrees from 360, the remaining angles will be added, and that will form the arc length of what we want. Now, if you look at this line, this is 1/8, a straight line. That means that from the total angles on this line straight, this is half a circle, this is a quarter. This will be 180 degrees. This will be 90 degrees. So if you add 180 plus 90, then you multiply, you express as a fraction of 360 and multiply by the circumference of a circle. You will get the arc length described in a 3/4 of a circle. Let's see that and see what happens. So C will be equal to 270 degrees all over 360 into 2 pi r, where r is the radius of the circle and the whole of this is circumference. Let's divide by 90 by 0 0 by 9 3 by 9 4. You get 3 out of 4 multiplied by 2 pi r. By 2 1 by 2 2. You get 3 out of 2 pi r. And this is the arc length of 3/4 of a circle. And you'll appreciate from what we did earlier on, this part formed the arc length we are discussing. This is the arc length we are discussing. So you can see that from the three arguments, we can now develop a general argument. From what we defined here, suppose this angle is not 90, neither is it 180, neither is it 270. It is just an angle. Then what do we do? And we have been told to find the arc length. So if this angle generally we call it by a letter, let's say theta. We call that angle theta, where theta defines any angle. And that theta exists between the range 0 less or equal to theta and theta less or equal to 360 degrees. It must not exceed 360 degrees. It must not go below 0. It must exist within that range. So this angle is the general angle we are talking about that we want to use to define our what? Our arc length. So generally, we are going now to have, for any arc length, of a circle, comma, L defined by arc length is equal to theta over 360 degrees into 2 pi r. This theta can be 90 degrees, it can be 180, it can be 270, it can be 60, it can be 50. This will define our arc length, which now, when we simplify, let's now do the simplification. By 2, 1, by 2, 180. So class, we obtain pi r theta, because multiplication in mathematics is what we call commutative. You understand the term commutative? I can interchange the position of what? Position of multipliers, but still get the same answer. Multipliers, but still I obtain the same answer. That means 3 times 4 is equal to 4 times 3, which is still 12. That's what we mean by commutative nature of multiplication. So when I bring this theta the other side, it still gives me the same answer. all over 180 degrees. And this is the formula that we shall be using to calculate the arc length of any arc of a circle. So we now say generally that L, which is arc length L, where theta is the angle subtended at the center of a circle, and R is the radius of the circle. Good evening, class. That marks the end of our lesson today. We have derived the formula for finding the arc length of a circle. In our next class, we are going to see now how we do application of arc length into related life experiences in terms of circumference and arc lengths of circles. I've enjoyed your class. You are a lively class. Have a good evening.